We can do that. We can absolutely do that.
Like, you look at the time.
Hi, Shandy. Hi, Shandy. I'm videoing this for you. However, there are 2 other people that aren't here, so I'll put this in YouTube
Are we even
tonight.
on?
I don't know where we are. I couldn't remember where we
No,
left
we're
off.
Organic versus inorganic.
Yeah, we're on
Are we past this?
organic
No,
versus,
we're
no, we're
not.
before that.
Oh, we're before this.
We're organic versus inorganic. Only because I've been highlighting.
No, that's fine. That's what I couldn't remember. Oh, gosh.
Next one.
Right here.
Yeah, right
All
there.
right. Fabulous. All right. Okay, so this is to the point in the notes where, we've done a little bit of some basic chemistry, and now we're going to start getting into important compounds. And so in order to differentiate from those, we need to talk about the difference between organic and inorganic compounds. And give me just a second while I find where I am in my notes. There I am. Okay. Organic compounds have carbon and hydrogen. We used to always say that organic compounds only had carbon. That's kind of a standard high school statement, but now as we move on, organic compounds are going to have carbon and hydrogen. Carbohydrates, lipids, proteins, and nucleic acids are the 4 most important organic molecules. Okay, and those are the 4 that we concentrate on, the 4 organic compounds that we concentrate on for the majority of the rest of this chapter. Okay? Now, inorganic just means they could have carbon or they could have hydrogen, but they just don't have both. So when I think of an inorganic compound, I think of water as being the most important. And if you've looked at your notes, you'll notice that there's a lot of information about water. Brittany, are we good? Yeah. Okay. Carbon dioxide, you guys know what that is. We're breathing oxygen. We will also talk about acids and bases, which are inorganic, and some important properties about those as we go. Okay. All right, so we talk about water. Like I say, it is probably the most important inorganic compound there is. It is known as a universal solvent, which means that there are a gazillion things that will dissolve in water. Like, we actually differentiate between things that are water soluble and things that are lipid soluble, lipids meaning fats. So there are just a ton of things that are water soluble. Water is also important for reactivity. So our body is mostly water, and you guys probably already know that. And there are all kinds of chemical reactions that go on in our body. Well, they couldn't go on in our body without us having so much water, which is why you always hear, how bad it is to be dehydrated for lots of reasons. But one of the reasons is because if you don't have enough water in your cells, then you've got all these chemical reactions that can't take place in your body. So water allows reactivity to take place. High heat capacity means that water can absorb and retain heat very easily, which is why our body temperature truly doesn't change a whole lot. Okay, so even if it's 100 degrees outside, your body's going to be able to sweat, to release water, to evaporate heat, so that our internal body temperature just isn't going to change a whole lot. So this is a big thing. And and the other thing, if you think about the stability of heat, you know how long it takes to boil water. If you've ever sat and had to make Kraft macaroni and cheese, and it takes forever, because it takes so much energy to literally raise the temperature of water. So
Why does salt, when you put it in there, make it go quicker?
that, my dear, is a fabulous question.
You do that, though, at home, don't you?
I don't.
I do, and it makes it go quick. It's like,
Do you think?
I don't, because it makes the noodles stick together.
I put oil in it, too, though.
Honestly, I thought the salt was just for a flavor thing.
No. it actually makes it boil quicker. Do you think it's because it absorbs the?
Hey, I have a great idea. You guys can look it up, email me the answers, and I can give you a couple extra points on this test. Oh,
Okay.
I think that sounds like a fabulous idea.
Why does salt
I'm good with that.
make
I'm
water
fine with that.
boil
Just
quicker?
email it to me sometime, like in the next week. I think it sounds like a. Shh, don't tell anybody, except everybody else in the class. Did you guys hear that? Okay.
Thank God for college comp, or I wouldn't be ready for this.
You what?
I said thank God for college comp because now I know how to save a link and put it in an email.
Oh, good. Good.
I have like actual stats.
And then, of course, water is for lubrication, and more, instead of the word lubrication, I would literally use the word moisture for more so than lubrication. But these are all really important properties of water. Most of our body weight is water. Key structural and functional component of cells. In other words, most everything in your body is water. That's really all that you need to know from that slide. Okay. So remember on Monday we talked about ionic bonds and covalent bonds. Okay. So ionic bonds will dissociate or ionize in water. So think about salt. You put sodium chloride in a glass of water. You stir it up, the ionic bonds break, and what you have left are ions. You have a positive sodium ion and a negative chlorine ion. That's ionization, which is the same thing as dissociation. Okay? They mean basically the same thing. Inorganic compounds that will do this in water are called electrolytes. You guys know, you've heard about electrolytes, and when we sweat, we need to replace our electrolytes because in our bodies, these ionic compounds will dissociate in water, and then we sweat, and then we lose them. So in order for everything to function properly, we need to replace those. That's why Gatorade was invented. It was invented as a way to replace those electrolytes. What they have found out about Gatorade and Powerade and all those over the years is they're nice and sweet, and kids like them, but the sugar defeats the purpose. So for a lot of years there in sports, they cut the amount of Gatorade in half. They cut it with water in half. Well, then they were finding out that even that amount of sugar was too much. Kids were still getting dehydrated. And the majority of high school sports anyway, and I can't necessarily speak for college sports or professionals, but I know the high school sports that I've always been associated with, they're giving the kids water, not Gatorade anymore, because it just had too much sugar in it. But electrolytes will actually conduct electricity in that solution too. Okay. Electrolyte imbalances can cause lots of things. Muscle cramps is the biggest one. Whenever I'm sure you've seen athletes cramp up on a sports field, football players especially, and what?
Especially when you're potassium.
Yeah, I was just gonna say, yeah.
I've
And
had that happen.
yeah, it's tough. They can't really quickly replace the potassium on a high school field for sure. I watch our kids; they stretch them out and they just load them up with as much water as they can. But I always, and what have you ever eaten before a sporting event or before something that you think you're going to be dehydrated so you don't get cramps?
Pickles.
No. Oh yeah, you could.
I eat salt. Like if I feel like.
How about bananas? Didn't we talk about bananas Monday and somebody hated bananas?
Yeah.
Wasn't that it?
Well, no, she told us a fun fact about.
Oh, that was
bananas.
right. But I forget what it was now.
You get more radiation.
Oh, that's right. You get more radiation from a banana. So you're going to glow in the dark, but you won't get muscle cramps. There, eat a banana. There we go.
Salt will also raise your blood pressure.
That it does raise your blood pressure, which is a bad thing. This just shows you basically what's happening to an ionic compound in water. You will not have to label this or anything for the next exam. I already checked, so let's just move on. These are the important electrolytes that will dissociate or ionize in your body fluids. So sodium chloride, salt, you guys know that. Potassium chloride, calcium phosphate, sodium bicarbonate, magnesium chloride, sodium hydrogen phosphate, and sodium sulfate. All of these,
Do we need to know the initials for that? Like
no.
KCl, or do we just need to know potassium?
I was actually just going to tell you, this is more of kind of a fun fact than a on the test, not on the exam. So don't worry about them. But if you ever wanted to know, besides sodium chloride, what other electrolytes are in your body, when these dissociate, these are all the electrolytes. So if you ever check a bottle of anything like a Gatorade or a Powerade, just out of curiosity, see what of those are in there. I mean, if you've only got maybe sodium and chloride and nothing else, then what would be the point? So just kind of be aware that anything it tells, or what are you drinking, Powerade? Body, what is that one?
Oh yeah, that's new.
Oh,
Potassium.
well, tell us what's in there.
1,240 milligrams of potassium.
Potassium.
Antioxidants, B vitamins. I was actually in the wrong part. Potassium, vitamin A, vitamin C, vitamin E, niacin, vitamin B,
Those are all,
vitamin B12,
those are all vitamins.
magnesium, zinc.
Okay, you got magnesium, and you got, what did you say there was sodium in? No, what? Potassium.
Zinc and
So in that sports drink, the only electrolytes that you would be replacing are magnesium and potassium. That's it. So would you suggest that an athlete drink that during a big sporting event? No, I wouldn't either. All it's giving you is vitamins. Vitamins are great, don't get me wrong, but for replacing electrolytes, don't need them.
it was on sale and it tasted
Oh, it was on sale and it tastes good. Well, there you go. There you go.
Actually, they were really good if you
Okay.
did
The terms hydrophobic and hydrophilic. What that means is there are some things that are water loving and there are some things that are water hating. And I'm going to give you there's lots of examples, but I want to give you the example of cell membranes, okay? Brittany, oh shoot, hold on. I
I'm
forgot.
still here.
Huh?
I'm still here.
Can you, if I come over here, can you see me?
No, oh yeah, I can see there.
Right here? Okay. But this can't see me. There. Okay. Cell membranes. Cell membranes are what we call a lipid bilayer. It is made of lipids that have one end that is water loving, hydrophilic, and one end that is water hating, hydrophobic. And so what that means is, let's say that wasn't very good. This is part of a cell membrane. This is the outside of the cell, this is the inside of the cell. Surrounding your cells is a watery environment. Inside your cells is a watery environment. You don't want your cells to dissolve in water, right? So we need the hydrophilic ends of the molecules to be facing out or to be facing the watery environment. So these are phospholipid molecules. What I'm going to color in red, these are the water-loving ones. These are hydrophilic. They're like, hey, there's water all around me. I'm so happy. These tails are hydrophobic. They don't like water at all. So they need to be pointing inside. Otherwise, your cell membranes would dissolve. So this is just one example of a place where you would find hydrophilic and hydrophobic molecules, but this is probably one of the most important ones. Water loving, water hating. Okay. Do you know these terms? What's a solution? What's a colloid? What's a suspension? What's an emulsion? Do they ring a bell? Do they not ring a bell? Sort of, kind of. Okay. So mixtures with water can come in different forms. A solution is any kind of a solute mixed with what we call a solvent. Think of water as the solvent. Remember how I said it's the universal solvent? Ever made Kool-Aid? Of course you have. Kool-Aid powder would be the solute. So let's say that I have a canister of pre-mixed powder. I don't need to add the sugar. Sugar's already in. and then I've got water. The pre-mixed powder is the solute. I've got the water, which is the solvent. I mix them together, it dissolves, and I have my favorite red Kool-Aid. Okay, that is a solution. We usually talk about solutions with regard to concentration, and we'll get to that a little bit later. But saturated, supersaturated, things like that. Okay, but we'll get to that a little later. A colloid is a mixture of organic molecules that have proteins in it and water, and a colloid would be Jell-O. Okay, so colloids have that kind of a consistency. The protein substance mixed with water gives you a Jell-O texture. A suspension is where you have different types of cells or different types of substances in a solution, and the heavier ones bottom out and the lighter ones go to the top. Easiest example of that, you're all in the medical field, what's the easiest example of that?
I've seen urine that way.
Really?
Like kidney stones go to the bottom.
It's a lot of
In the-
Well, I was thinking blood.
The slimy stuff goes up to the top. Do you want to know that?
No, it's okay.
See,
I was thinking blood.
I was thinking amalgamants a lot.
Oh, okay. The red blood
I should have
cells go
known. You
down.
guys would have way better examples than I would. I'm just thinking blood.
Are you talking
Alright.
about how the red blood cells all flow to the bottom?
Yeah,
and
so-
and the plasma.
Yeah,
goes to
so
the
in
top?
a suspension, larger particles settle out. They go to the bottom. So if you drew my blood and you just let it sit there for a couple hours, the red blood cells would all go to the bottom, then the white blood cells, I think, and then the platelets. So that is a suspension. I had another example in my head and I've already forgotten it.
What
It'll-
about like sugar in cold water? It doesn't really dissolve; it sits there. Or sugar in milk. You know, like if you put sugar over
I've
your
never
Cheerios.
put sugar in milk.
And over like your Cheerios.
Your cereal?
Yeah. And then you eat all your Cheerios and there's
You-
still sugar.
Well,
just
honey, you
sitting in
probably just put too much sugar on there. It was probably super
I got
saturated.
it, don't worry.
Probably just super saturated and you put so I don't think so. Last one is an emulsion. This is like oil and vinegar dressing. Okay, an emulsion, one liquid literally suspends in another liquid.
They won't mix,
They won't mix.
no matter. if
Well,
you shake 'em.
temporarily.
Yeah. and then
Shake
they
them up,
separate
temporarily
them.
mix, yeah, and then they won't anymore.
Won't stay.
Yep, they won't stay mixed. Won't stay mixed. These pictures are just of the things we talked about. There's they use mineral water. I think Kool-Aid's a way better example of a solution. There's my Jell-O that's a colloid, and there's blood as a suspension. Okay?
You know what's really cool?
No, but I'm sure you're going to tell me.
I am. The plasma at the top.
Yes.
It gets separated
Yes.
in the centrifuge and the red blood cells
Uh-huh.
at the bottom. Do you know what the middle layer is?
The white blood cells, aren't they?
The Buffy coat.
Oh yes, the Buffy coat. That is
You
right.
ever heard of that? I had to
I
pull
have,
one
yes.
of those off, and I was like, what in
Yes.
the heck is a Buffy
Yeah, I
coat?
forgot about that. Yes, it is.
It's like a gray little
It's a little line.
gray line that goes through. It
Yeah, I have
separates
heard
them.
of that. I've forgotten
It's
about it,
called
but yeah, it's called the Buffy coat.
It is so cool.
Yeah. Yeah.
Anyways.
Okay.
Fun fact.
So that's all about water and all of the different mixtures that you can have with water. Any questions on that? All right. pH. Are we familiar with pH?
Yeah, Sharon.
What?
Well, I mean the pH in your urine.
Oh, yeah, okay. I thought you
Yeah.
said Sharon. I'm like,
No,
who's
your-
Sharon?
Urine.
Urine. Yes, urine. Absolutely. Okay. Do you know what pH is though?
It's the
level of acidity.
Yeah, see, that's what you're measuring acidity, but why are some things considered acidic and some things are considered basic? It has to do with ions. So see, we talked about ions before. Now pH has to do with ions. It has to do, this must be on the next, pH is the measure of hydrogen ions and hydroxide ions. Usually, I guess we just say hydrogen ions, but there are two ions. pH is the measure of the amount of hydrogen ions versus hydroxide ions. Hydrogen ions versus hydroxide ions that a solution has. Yep. pH is a measure of the amount of hydrogen ions versus hydroxide ions in a solution. And don't worry, we'll get to that. We'll get a little more into that. Do you remember or know what numbers the pH scale goes from? From what to what?
0 to 14.
Technically 1, because technically there isn't anything that's a 0 pH. But yes, 1 to 14. So the pH scale goes from 1 to 14. And the scale is actually logarithmic. And I will tell you that there is a question on the next exam where it gives you some examples. So let's just talk about pHs of 4, 5, and 6. Okay? This is on, by the way, this is on the acid end of the scale. Get to that in a second. If I measure something that has a pH of 6, it is going to be 10 times more acidic than 7. So we got 7 is here, pH of 6 is 10 times more acidic. Go down to 5. Now we're 100 times more acidic than 7. Go down to 4. Now we're 1,000 times more acidic than 7. So for each number of the pH scale, whether you're going down or up, it is a logarithm of 10 times. So what if I said, what if we started at a pH of 6? And I wanted to know how much more acidic a pH of 3 would be. So I'd go from 6 to 5 would be 10 times. From 5 to 4 would be 100 times. From 4 to 3 would be 1,000 times.
Oh, 4 to 3.
If I started at 6, 6 to 5 would be 10 times. 5 to 4 would be 100 times. 4 down to 3 would then be 1,000 times. Hint, hint. Just saying.
And then
That would be a
3 to
really
2
good example to know.
3 to 2 would be
10,000, yeah. Any substance that is neutral has the same amount of hydrogen and hydroxide ions. And neutral is considered 7 on a pH scale, or thereabouts. 6.8 to 7.4, somewhere in there is neutral. We always just use whole numbers when we're talking about it, but anywhere in that range. Okay, acids have a pH of 1 to just less than 7. Acids, we call them acidic. They have a pH of 1 to just less than 7. Acids have more hydrogen ions than hydroxide ions. They have more hydrogen ions than hydroxide ions.
On the test, is it going to be these abbreviations or is it going to say hydrogen and hydrogen oxide?
It'll be abbreviated.
It'll be abbreviated. Okay.
Basic pH is just above 7 to 14. Just above 7 to 14. And bases have more hydroxide ions than hydrogen ions. So if you think about an acid, lots of hydrogen ions, very few hydroxide ions. Think about a base, lots of hydroxide ions, not as many hydrogen ions. Neutral at 7 has an equal amount of both. So if I asked you a question and I said, what has a high amount of hydroxide ions? Would you say an acid or a base?
A base.
Correct. Hint, hint. Here's a typical pH scale. You'll notice that the acids, and here's the other thing. Your textbook goes horizontally. A lot of textbooks do a pH scale vertically. If you happen to, and I don't know that there is a picture of it on the exam, but if in any other class even, you happen to come across a pH scale that is vertical instead of horizontal, don't let it throw you off. Okay, like the ones in my textbooks that I use in high school are vertical. So this is unusual for me. 1 to almost 7, acids, more hydrogen ions. Above 7 to 14, bases, more hydroxide, less hydrogen. Interesting fact, most of your cleaning supplies are bases. I think a lot of people think, oh, they're acidic, they're going to get rid of all kinds of germs and this and that. Most cleaning supplies are bases, which I always think is kind of interesting. pH of blood, about 7.4, by the way, so it's pretty neutral. Pure water is here. Blood's pretty neutral. Eggs are pretty neutral. Saliva, milk, those are all pretty neutral. Blood should be about 7.4. Yeah. Yeah. Kind of interesting. This, tomatoes right now, and all my tomatoes are ripe, and I keep eating tons of tomatoes out of my garden. I'm sure there have been days when I've had 2 or 3 tomatoes right out of the garden that my pH in my blood may have dipped just a titch.
We can actually diagnose sepsis in the field.
Oh yeah?
With acid base.
Really?
A test called capnography.
And so what do you test, or what?
Blow off, and how much carbon monoxide you blow off and stuff like that. You can tell the higher level. So the normal range is between 35 and 45.
Okay.
If you're higher than 45, you're blowing off or you're retaining too much CO.
Oh.
And you're not breathing well. And if you're blowing off, and your numbers are low, you're basically going to make yourself pass out because you're blowing off too much CO.
Interesting.
So we can use that test and pretty much judge whether somebody's septic or not.
Interesting.
And there's a whole nother. I mean, it just goes deeper into the procedure, but yeah, we can do that with tests in the field.
I've now learned something. Interesting.
I might do it today.
There you go.
Kidding.
These are just examples of if you have an ACE and an acid and they dissociate. You'd have a hydrochloric is an acid and it dissociates. Potassium hydroxide, you end up with potassium ion and a hydroxide ion. Salts are potassium chloride would be a salt. Notice there is neither hydrogen nor hydroxide when that dissociates. You don't need to know that for the test, however. Okay. Acidosis and alkalosis. You guys, again, probably in the medical field have used those terms, I'm sure more than I have teaching. Acidosis, you have a really low pH. You have too many hydrogen ions in your bloodstream especially. It's acidosis. Alkalosis, your body fluids have too much hydroxide ions. And again, your body, remember how we talked about homeostasis? Your body doesn't like either of those to be out of whack. Not hydrogen, not hydroxide. It will start affecting all of your organs if you have too much or too little of those. So pH is too high or too low, damage to cells and tissues. Alters proteins, which is a big deal. Proteins are what make you you. DNA contains the information to make proteins that make you you. And so you start messing with the pH in your body, it's going to start affecting the proteins that make up everything in your body, your cells and your muscles and your brain and everything else. So too acidic or too basic can start altering the proteins. Starts messing with your bodily functions and eventually organs will shut down. So got to keep our pH nice and normal. The good news is for most people, our bodies do a good job of that. Your kidneys are one of the big players in this, keeping your acid and bases at a nice even level. So it's not like you have to, don't wake up in the middle of the night and worrying about this, okay? You're good. Here we go. Salts, when they dissociate, they're going to give they're going to give positive and negative ions. But like I said before, they don't contain any hydrogen or hydroxide ions. So that's how you know whether you are talking, whether you need to worry about becoming acidic or basic. If you've got a salt that is dissociating, it's not going to affect your pH. Will it affect other things in your body? Of course it will, but it's not going to affect the pH in your blood. Buffers are what are going to neutralize acids and bases. I'll give you a for instance. So when the contents of what acid is in your stomach? Yes. Stomach acid. Thank you so much.
I'm like, is this a trick question?
No, what acid's in your stomach? It's not, I mean, we call it stomach acid, but hydrochloric acid is in your stomach. It actually has a pH of about 2 in your stomach. It's really acidic. So you've got that hydrochloric acid mixing with all the food in your stomach, and your stomach is designed for that. It's got a mucous membrane lining. The cells of the stomach replenish themselves really quickly, not a problem. But then the food moves from your stomach into your small intestine. Well, your small intestine is not designed to accept really acidic fluids. So as soon as the food goes from, the chyme goes from your stomach into your small intestine, there's a hormone called CCK, and CCK sends a message to your pancreas. And not only does your pancreas secrete insulin, but your pancreas also secretes a buffer. And that buffer will immediately neutralize that acidic chyme that goes from your stomach into your small intestine. For most people, it works perfectly fine. For those people that produce way too much acid, people that are way too stressed or have digestive issues, that's when they get an ulcer in their small intestine. Ulcers in your small intestine are actually more common than in your stomach because your stomach's designed for the acid.
So that's kind of like they can't get rid of that
Hydrochloric acid.
And there's too much of it.
Too much of it.
goes
Their
up
buffer, their pancreas is probably secreting a buffer, but they're producing way more acid than
so
they
it
should.
goes up their esophagus and all that.
It
too.
can.
Okay.
That's kind of a
Causes
different.
heartburn.
That's kind of a different story. That's acid reflux, which is before it gets to the small intestine. But yeah.
Okay.
Yep. So anyway, buffers neutralize strong acids and strong bases. Okay. Any questions on pH? Okie dokie. So now what we have the 4 types of organic molecules. We're going to have carbohydrates, lipids, proteins, and nucleic acids. And we'll talk a little bit about what they're made of and what they do and some things like that. So I don't remember if and I don't remember whether this is in your textbook or not, but I think it's just something good to picture. So organic molecules are macromolecules, big, macro meaning they're big molecules. Sometimes we also call them polymers, meaning many units go together. Every one of these has a monomer, meaning it has a little unit or several little units that will bond together to make a big macromolecule. Okay? So for instance, probably the easiest one, do you guys know what make up proteins? Proteins are made of, do you guys know? Amino acids. Proteins are made of amino acids. And you hook tons of amino acids together to make protein. So what are the monomers that make a protein would be called amino acids. They're just little units. So all of these have small units that we hook together to make the big molecule. So if I use the term, and like I say, I couldn't remember whether in your notes it talks about monomers or not. So if it does, if it doesn't, and I use the term, I just kind of wanted you to be aware of what it is. Okay? Think of it as you're building a big Lego mansion, and each Lego is a monomer, and your macromolecule is Lego mansion. Okay. Okay. Oh, it does say monomer right there. Oops. There we go. Yeah. Made of monomers. Okay. Mono meaning one, poly meaning many. Every organic compound has what's referred to as a functional unit. This is a way more chemical than you need. we're not going to worry about that. Okay, let's start with carbohydrates. Carbohydrates are the main source of energy for all living things. Carbohydrates are made of carbon, hydrogen, and oxygen. Carbohydrates will always be in the ratio of 1 to 2 to 1 of carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. Glucose is a monomer of a more complex carbohydrate. Okay, so glucose is a carbohydrate. The chemical formula for glucose is C6H12O6. These three elements are in a ratio of 1 to 2 to 1. Okay, that is a very, very common thing to see on tests, or at least to know. Thing about carbohydrates, this is what we use for quick energy. There are also carbohydrates that make up cell membrane. Structurally, they look like this. Carbons, hydrogens, oxygens. You won't need to know any of the structural formulas for it. Now, have you heard of monosaccharides or disaccharides or polysaccharides? Okay, mono means what? Mono means one. Great. So, simple sugars are monosaccharides. Simple sugars are glucose, fructose, and there's actually one more. There's galactose. I guess your book doesn't have it. These are simple sugars that are going to be bonded together to make more complex carbohydrates. Chemical formula, glucose, fructose, and galactose are all C6H12O6. They're in a ratio of 1 to 2 to 1. They have different structures. If I gave all of you 30 Legos, you'd have 10 green, 10 blue, 10 red. Your formula would be the same, but you'd all build something different. That's what I mean by different structural formulas. So glucose, fructose, and galactose are all C6H12O6, but they have different structural formulas. We don't eat glucose. We don't eat fructose as it is. Remember, these are monomers. They're going to bond together to make more complex carbohydrates. Like, for instance, in that banana that some of you don't like that is going to cause us radiation. Bananas are sweet, right? Well, the sugar in a banana is made of glucose plus fructose. So these are the monomers that would be bonded together to make a polymer called maltose. Table sugar, what you put on your Cheerios and mix it with your milk that apparently you put too much because it doesn't dissolve, that's sucrose. Sucrose is, I believe, sucrose is just a bunch of glucose molecules hooked together. We don't just go to the store, I'm going to go buy a box of glucose. You don't. Now, you can buy glucose tablets. Why would you want to buy glucose tablets?
That's for
Diabetics, sure. So think about this. These monosaccharides, simple sugars, get into your bloodstream really fast. So if a diabetic is having a crash, they need to get sugar into their bloodstream really, really quickly. Glucose will do that. It gets into the bloodstream really quickly, but then it gets used up fast. So that is just a quick fix. That's not what we want to eat to sustain our lives. We want to eat more complex carbohydrates that we've added all these together.
So, you said you don't just go buy these things, that they're mixed together. So what is high fructose corn syrup?
High fructose corn syrup is a combination of, I think it is,
Or more commonly, why is it fructose then?
because it would be a combination. I think it's a combination of glucose and fructose. Oh wait, high fructose corn syrup. No, it's not just straight fructose, I don't think. I could be wrong on that, but I don't think it is. Or it's
I was just curious why fructose is in the name,
high fructose corn syrup. I don't know that it is necessary, although it could be because it gets used up really, really quickly.
but not. I just know all my Dole fruit cups.
Yeah, high
Advertised.
fructose corn syrup. It's a simple. It could be. I didn't even think about that, to be very honest. High fructose corn syrup. I'll have to think about that. And is it just strictly fructose, or is there some gluten? I'll have to get back to you on that one. But no, it's a great question. I'm not sure. Were you gonna ask something?
Pertaining to the slide, the way it's reading, so glucose is that, fructose is that,
Mm-hmm.
is fructose, are they saying both of those is an isomer?
An isomer?
Or isomer of fructose is an isomer of glucose.
Yeah, meaning they're similar.
Similar.
They're both simple sugars.
Okay.
They both get used up really quickly. And now that I think about high fructose corn syrup, but corn has sucrose. I got to get back to you on that one because I don't know. Sorry. Okay, so if we take those simple sugars and we just combine any two of them, we have what's referred to as a disaccharide. So think about word parts, think about prefixes.
Two.
Yep. Glucose and fructose makes sucrose. That's what we're putting on our cereal. Glucose and galactose makes lactose. Where do you find that? In milk, ice cream, all that good stuff. Yep. And then glucose plus more glucose makes maltose. And that's what starches usually break down into maltose.
I'm thinking of the malt balls.
Ooh, I like malted milk balls. You're going to put that sugar on your cereal, and you're going to eat it, but in order for your body to use it, that sucrose needs to be broken down in your cells into glucose and fructose. That's where cellular respiration takes place in your cells. 7:19, I got to speed up. Okay, speeding up. You don't need those. Okay. Polysaccharides are even more complex. We have the monosaccharides, we got disaccharides, now we got polysaccharides. Polysaccharides are the most complex carbohydrates. Cellulose is what's in the stringy stuff in celery? That's cellulose. That is a polysaccharide, and its job is to provide energy. Starches in like potatoes. Starch is a polysaccharide. We eat potatoes, and then your body needs to break those polysaccharides down into monosaccharides to get energy. Animals can store starch. Animals actually store starch in the form of glycogen. And that glycogen is stored in your muscles and in your liver. So even if you are even a carnivore, an animal that literally only eats meat, is still able to get some starch because that starch is stored in muscles and in your liver. So any animal that's a carnivore is still getting some starch. It's in the form of glycogen. Now, we have glycogen in our liver as well. If we are not we're doing one of those really bad diets and we're not taking in any starches because we think we're going to lose 5 million pounds and we're going to do nothing but keto. And I know. Tried that, by the way, and then my gallbladder had an issue, so I had to have my gallbladder out, just saying. Your body still needs carbohydrates to function. As a human being, we need carbohydrates. So if your carbohydrate intake is really, really low, eventually what's going to happen is your body's going to start accessing the glycogen in your muscles and in your liver to try to break that down to get some carbohydrates. It's really difficult for your body, so it's hard on your body. Okay, moving on. That's what it looks like. You don't need that. Trying to think hold on. Don't. Okay, I don't believe there are any questions on the exam about this slide, so for the sake of saving time, I'm going to move on, okay? I will double check that before you have your next exam, but I'm 99% sure no. Okay, that was carbohydrates. Let's move on to lipids. Lipids is just a fancy word for fats, but it's also oils and waxes. They're hydrophobic, meaning they don't like water. You guys know that. Lipids are mostly carbon and hydrogen. There is a little bit of oxygen, but it's mostly just carbon and hydrogen. Big thing about lipids, this is what your cell membranes are made of. This is also a place for stored energy. Because you're also taking in carbohydrates, which are providing quick energy. If your body can get quick energy, it's hard for your body to get the energy out of those stored fats. Yeah, trust me, I know, but I know. Your body's like, oh man, that is going to be so hard to get that energy out of there. Maybe we should just tell her to eat a Snickers. Yeah. These are all of the different classes of lipids, okay, different groups of lipids, and we're not going to take the time to do all of them, just some of them. The monomer, or the small units that go together to make up lipids, they actually have two. It's glycerol and fatty acids. Is that on here somewhere? No. It's not. But that's what it is. I'm going to write that down for you. But it's not on here, although I don't think it's on. I don't know. I'm going to write it down for you because I don't remember if it's on the exam or not. The two monomers that make up lipids are glycerol. Glycerol.
Oh, I was going to say they have glycerides.
Same thing. And fatty acids. Glycerol and fatty acids are the two monomers that go together in lots of different ways to make all of these lipids. You have probably heard of saturated and unsaturated with regard to probably butter, would be my guess. Saturated and unsaturated fats in foods and stuff. It all has to do with the number of covalent bonds between carbons. Let's just put it this way. Saturated fats you find in things like lard, butter, usually in animal fats. Those are artery clogging. Unsaturated fats with lots more covalent bonds changes the shape, and it changes how your body metabolizes it, and it's actually easier for your body to metabolize. So think olive oil, a little more healthy for you. That's unsaturated. Monounsaturated, one double bond, that's good. Polyunsaturated, even better. More than one double bond. So olive oil is a polyunsaturated fat. It has lots of double covalent bonds. It's actually liquid at room temperature. Usually saturated fats are solid at room temperature. So think about lard, think about butter, although butter's delicious. Butter's really not all that bad for you, and just don't go deep frying a thing of butter and then trying to eat it. That'd be bad for you. Okay, polyunsaturated, think olive oil. Liquid at room temperature, won't clog your arteries as much. Oops. Oops, wrong way. Ah! Gush, gush, gush. Oh, it's because I was hitting the wrong thing. What? Monounsaturated would be, honestly, I don't even know an example of monounsaturated. And the good news is you don't need to know it.
Okay.
Wait. I thought mono and poly were different. Why are they both only one double bond?
One double bond, more than one double bond.
I was looking at it as an arrow.
Oh, I didn't see
Greater
that either.
than, more than one double
More-
bond.
I'm going to write that out more than.
You're
I didn't
welcome.
see that either.
Okay. You know, we've all
I'm
been.
like, okay, she said that one was even
Yep.
better, but I'm like,
Okay.
okay.
That's that. So here's where the monomers come in. This talks about glycerides. Glycerol is bonded to, or fatty acids are bonded to a glycerol. That's where I said these are the two monomers that make up lipids. Don't worry about that stuff. Functions of these lipids, energy source, insulation, protection. Our fat is protective, which is why females have an extra layer of fat so that we can protect the babies, whether we want to or not, whether we have them. That was terrible. I didn't mean that. Oops. I meant, sorry, I turned off for a minute. We're good. But whether we happen to have any babies with us right now or not, which is also why men can lose weight so much easier. Damn them. Drives me crazy. Yeah. Here's what you do need to know, though. That fat storage molecule is a triglyceride. Fat storage molecules are triglycerides. They're actually going to store lipid as droplets inside your cells. Now, the good news is there are certain medications and certain vitamins that are lipid soluble. So you do need some lipids and you do need some triglycerides. Like vitamin A, vitamin D, vitamin E are all lipid soluble. If we didn't have triglycerides in our cells, we wouldn't be able to absorb those. Now, the bad thing is triglycerides also absorb drugs, toxins like pesticides, things like that. So it's like anything in your body. There's good and there's bad. But we all have triglycerides, and they're the fat-storing molecule. Got 20 minutes. So eicosanoids are a lipid that we can't make in our body. You can only get them from things that you eat. Couple of reasons why they're important. Leukotrienes are eicosanoids that you need for your immune system. And then prostaglandins are actually hormones. They're what we refer to as local hormones. They don't get secreted into your bloodstream and travel around your body. They literally just get secreted in a particular organ and stay in that organ. So you do need these. We get them through a balanced diet. Not typically something that most people have to worry about. Oh my gosh, did I get enough eicosanoids in my diet today? Any kind of a healthy fat, usually you can pick those up, okay, in your diet. Not something to worry about. Okay, moving on. Steroids are the last kind of lipid that I want to talk about. It's a lot of red because all that's important. Steroids are a type of cholesterol. Yes, you know there's good cholesterol and bad cholesterol, right? Steroids are a type of good cholesterol. It is a lipid. Cholesterol is needed for lots of things. You have good cholesterol in your cell membranes. So if you've ever had your cholesterol tested and they've told you what your good cholesterol is and your bad cholesterol, well, your good cholesterol needs to be at, I honestly don't even remember the level. I don't even know if I've ever had my tested.
Well, they're testing that right now, but they think anything above 70 is actually, the higher the better.
Okay. Good cholesterol you need for your cell membranes. You need the good cholesterol also so that we can absorb vitamin D. And as women, you know that we need to absorb vitamin D to keep our bones strong because as we age and our estrogen levels decrease, we don't absorb calcium as well and our bones become brittle. So we need that good cholesterol. Oh, yeah.
They also think it fights off your LDL. Like they think that the
Yeah.
HDL is more important than
They
the
do. Good
LDL.
cholesterol will typically keep your bad cholesterol in check. Yeah, you also need, the combination of calcium and vitamin D. So, like at my age, I have what is called osteopenia, which is a precursor to osteoporosis, just because of my age. And so what I have done over the last I can't even tell you how many years, I take 10,000 IUs of vitamin D every week to help strengthen my bones and keep them strong. And they've actually seen, and then I have a bone density test every other year. And my doctor has actually seen my bones become stronger, except in the place
The little green pill.
where I broke them. No, I don't. I have something else. But
Oh.
okay. Some of the hormones that we have in our body, some are steroids, some aren't. Steroid hormones are sex hormones. Estrogen, testosterone are sex hormones. You haven't even studied these yet, but corticosteroids, calcitriol, they're steroids. Bile salts are also steroid derivatives. So these are just all some of the places that you will find steroids in your body. So something that you should definitely know is that steroids form steroid hormones. Okay, steroids can form steroid hormones. Not exactly sure why I wrote that there, but clearly I wrote it in red, so that
Probably
must
a
mean
agree or disagree question.
it could. Oh, that could be
Steroids can form.
hormones.
hormones.
So is that why people who take steroids get like roid rage because they have so
So-
many hormones?
Well, yeah. So here's what happens. Anabolic steroids are bad. So anabolic steroids are synthetic estrogen, synthetic testosterone. What happens when those people take synthetic testosterone, which are anabolic steroids, is your body says, "Oh my gosh, where did all this come from? Oh, I got to quit making it because we have too much." So your own natural anabolic steroids shut down, and you don't make as many as you're supposed to. So that then sets off a domino effect of things. So like in guys, if you have ever heard like Mike Tyson, his voice is higher because he's not producing his own natural testosterone anymore. Their private parts shrink, yes, because they're not producing enough testosterone anymore. It affects your brain somehow, and I don't remember what the exact thing it does in your brain is, but the roid rage comes from that synthetic anabolic testosterone affecting some part of your brain, the aggressive part of your brain. I don't remember exactly how that goes, but it's something along those lines. Okay? All right, I gotta move on. Okay, glycolipids, phospholipids. No, that's okay. I'm like, that's my alarm on my phone, but it's not it. I don't think there's anything on the test about that. Let's just move on because we're gonna run out of time. All right, proteins. Third kind of macromolecule are proteins. A lot of people will say these are the most important organic molecules in our body. They are definitely the most abundant. Proteins are what make you look and function the way you do. The monomer that makes up proteins is amino acids. In all of the world, there are only 20 amino acids. Those 20 amino acids in all different numbers, kinds, lengths, shapes make every single one of us different. They make every single one of us different from our dogs, from our cats, from the plant that you have on your desk. There are only 20 amino acids that make up proteins in the entire world. Almost all of your cell functions are carried out by proteins. So these are, that's probably true when they say that they're the most important organic compound. Here are all the places you find proteins and all the things they do. So there are structural proteins which provide support. So your muscles and your bones are made of protein. Contractile proteins, again, your muscles. They contract, they're made of protein. Transport proteins in your blood. Buffering, in other words, regulation of pH. Remember that buffer I told you that was released by the pancreas? It's a protein. If we didn't have that buffer, we'd all have holes in our small intestines. Enzymes are metabolic regulators. So, for instance, in your saliva, you have an enzyme called salivary amylase. Amylase is an enzyme. Enzymes are proteins. Salivary amylase breaks down carbohydrates from the time you start chewing on something in your mouth for about 3 hours into your stomach. Okay, and then there's proteases, which break down proteins in your small intestine. There's lipases that break down lipids in your small intestine. So all of these enzymes regulate all the metabolic reactions that go on in your body. Hormones are proteins. All of those hormones that we produce in our bodies. So you've got estrogen, testosterone, progesterone, insulin, calcitriol, calcitonin. I mean, the list goes on and on and on for all of the functions in your body. They're all made of proteins. And then last but not least, antibodies, which we all need, especially right now with COVID. We need these antibodies to fight things. They're all made of proteins as well. This just talks about the structure of an amino acid. Of those 20 amino acids, they structurally, they all look the same with the exception of this. All amino acids have this same blue group. They have a central carbon atom. They have a hydrogen here. They have this pink group. The only place they differ is this yellow square right there. It's different in all amino acids.
Did we skip?
Yes, I'm skipping.
Okay.
I'm going fast.
That's okay.
Sorry, I had to think here for a second. So in order to make a protein, let me back up. Amino acids are held together by what's called a peptide bond, okay? We talked about covalent bonds and ionic bonds and hydrogen bonds. Proteins are held together by yet another bond. It's called a peptide bond. So when we put a whole bunch of amino acids together, we call it a polypeptide. This happens by a dehydration synthesis. Okay, you'll probably want to make note of that. A peptide bond forms between amino acids by way of a dehydration synthesis. And Monday we talked just real briefly about those, all the different reactions. Dehydration synthesis creates the peptide bond which holds amino acids together. When two amino acids are together, it's just called a dipeptide. When you put a whole bunch of amino acids together, it's called a polypeptide. You put a whole bunch of amino acids together. Clearly, I forgot to color code this slide. Sorry about that. It's called a polypeptide. It is still, however, not a protein yet. It doesn't become a protein until it folds into a funky shape. All proteins have their own unique, weird shape. So during protein synthesis, we get this really long chain of amino acids, called a polypeptide. It then goes to a different part of your cell whose job it is to fold it into a funny shape. So the proteins that make up your muscles are one shape. The proteins that are hormones are a different shape. The proteins that are specific enzyme are a different shape. At that particular point, they're called proteins. There's actually 4 steps to that happening, and no, you don't need to know those. But, So this is like the first step. There's that big long chain of amino acids. And then it folds a little bit, and then it folds a little bit more, and then it folds a little bit more until it comes to its own shape. Now this is hemoglobin, by the way, which is in your red blood cells. That's one shape. This is collagen in your skin. So you can see they're both proteins, but they're different shapes. Okay. Skip this. Denaturation. Denaturation is when, because of too high of a temperature or pH being too high or too low, the shape of the protein breaks down. And if the shape of the protein breaks down, it can't do its job anymore. That is referred to as denaturation. Our temperature gets up to be 105, 106, 107. The proteins in our body start losing their shape. And then they can't do their job. And then you'll die. It's the easiest example.
Morbid.
What?
You just died.
I died?
He said it was morbid.
Oh, sorry. How enzymes work? Oh, yeah. Okay. I just need to see how much we have left. Good Lord. Okay. Enzymes. Simple explanation of an enzyme. An enzyme works like a lock and a key. One enzyme works on one chemical reaction. Here's my lock. Here's my key. That key isn't going to work on any other chemical reaction. So when you see the word here, specificity, that's it. There is no skeleton key enzyme. There is no generic enzyme. One enzyme, one chemical reaction, very specific. Lock and key theory is what that's called. Good enough. Whoops. This keeps. I'm back. This is what it looks like. Here's an enzyme, and let's say we need to do some kind of a chemical reaction where we're putting two things together. These two, and these are called substrates. These two substrates come in here, hook into the enzyme, voila, the enzyme super glues them together, and now we have whatever this product is. It'll work the exact opposite as well. You could literally do this backwards. You could take product, hooks into an enzyme, blowtorch breaks it apart, and then you end up with two things. So that's how enzymes work. Lock and a key. Here's the key, that's the lock, or the other way around. Cofactors, coenzymes, isozymes, we're skipping. Nucleic acids, last one. We've done carbohydrates. We have done lipids. We have done proteins, and now the last macromolecule are nucleic acids. DNA and RNA. That's what nucleic acids are. Did I skip a slide? No. Oh yeah, okay. If you remember DNA from way back in high school or whenever you had it before, a DNA molecule contains a coded information that makes you you, and it's in the nucleus. And the shape is like a twisted ladder, and we have nitrogen bases that pair up adenine, thymine, cytosine, guanine. Adenine pairs with thymine, cytosine pairs with guanine. The sides of the ladder are made of sugars and phosphates, and so then you twist it into this shape called a double helix. I'm sorry, what? Held together by a hydrogen bond, yes. Held together by a hydrogen bond. See, if you take a look at the very top, there is the side of the ladder in yellow, and then the nitrogen bases, adenine and thymine, and they're held together by a hydrogen bond. Okay. This is an RNA molecule. Now, RNA is only single-sided. DNA is two sides of a ladder twisted. RNA is half a ladder. DNA is in the nucleus, and DNA contains a code that makes you you. But in order to make the proteins that make you you, that information has to get out to your ribosomes. DNA is on house arrest. DNA is not allowed to leave the nucleus. So its cousin RNA actually copies the code from DNA, and then it has a special pass. It's allowed to leave the nucleus, and it goes to the ribosome where protein's going to be made. DNA's alphabet is A, T, C, and G. A pairs with T, C pairs with G. RNA has a little bit of a different alphabet. It has A, U, C, and G. Adenine, uracil, cytosine, and guanine. In general, these are the functions of DNA and RNA. DNA, the characteristics that make you you, its job is to direct the protein synthesis to make the proteins that make you you. Remember, enzymes are proteins, so that goes along with that. RNA's job is to copy that code from DNA, get it out to the ribosome. The monomer that makes up a nucleic acid is called a nucleotide. So this is the little unit that goes together to make up a nucleic acid. Nucleotides have three parts. There's a sugar, a phosphate, and a nitrogen base, and it looks like this. So this is, in DNA, it's a 5-carbon sugar called deoxyribose. This is a phosphate molecule. This is a nitrogen base. So this could be adenine, thymine, cytosine, or guanine, one of those. This whole thing together is a nucleotide. So you take one nucleotide, hook it up to another nucleotide, to another nucleotide, to another nucleotide on both sides to make that DNA ladder. If we're talking about RNA, it's just one side. But these three things are what the monomer that makes up a nucleic acid. Oh boy. These are what pairs together: adenine, thymine, cytosine, guanine. The guanine, uracil replaces thymine in RNA. Double helix. There is one other thing. There is one thing on this slide that you need to know. AMP. I know, I had to skip really fast because it's almost 10 till. AMP, adenosine monophosphate, is a nucleotide. And it is a nucleotide of ATP. What is ATP, you might ask? That's the energy source that makes everything happen in your body. Adenosine triphosphate. That's the energy source that makes everything happen in your body. I am so sorry I had to fly through that.
Energy source that makes
Everything happen in your body. And AMP, adenosine monophosphate, diphosphate, triphosphate. So it's like this. Here is, hold on, I gotta think real quick of the structure. It's got a sugar and a something. I can't remember exactly. Adenosine monophosphate would be one of these. Adenosine diphosphate is 2 of them, and adenosine triphosphate is 3 of them. When there's 3 of them together, they make ATP, and ATP is the energy that makes your body run. Okay? So when you think of a small unit that goes together to make something else, AMP is the small unit that goes together to make ATP, the gas that runs your body. Okay, I'm sorry I had to go so fast there at the end. Okay, you'll need your lab manual when we go to lab, and I will put this on YouTube. Probably won't get to it till tomorrow. Brittany, any questions?
No, but my son's caterpillar just came out of the cocoon and leaving.
That's awesome.